Next up we have Rob King. Rob works at the Antarctic Division and he has spent most of his working life studying krill. He spent extensive time at sea and conducting experiments in aquaria. Rob has unparalleled knowledge about krill, the krill life cycle and the krill ecosystem. Today he'll be talking to us about the RSV Nuyina's wet well capability, and Rob had a lot to do with the development of the wet well, and I'm really looking forward to hear from him today. Please, Rob.
Thanks, Alex. So RSV Nuyina bristles with over 140 separate science systems which are currently being commissioned right now. And all of these were off-the-shelf proven technologies except one, the wet well. And today I want to take you through why we thought it might be a good idea to put one on the vessel, how it went in initial commissioning, and what we think we might be able to do with it in the future. So the main driver for the wet well is the desire to catch krill in sea ice in winter, to get that elusive winter sample of krill. And traditionally we use nets, but if you deploy nets in sea ice, you are dicing with danger, because as soon as you catch some ice, you destroy not just the mesh, but the hardware as well. And as pressure in the pack increases, you can't even put it in the water because the engine thrust would destroy the net. So the Belgian and German teams put together the SUIT, the Surface Under Ice Trawl, and this was a brilliant suggestion because it went out under the ice beside the vessel and skimmed the krill off the bottom of the ice. It worked fantastically, but it could catch large lumps of ice, but it had a deflector. But the problem with it is that the krill came in packed in ice from the little ice crystals that were underneath the ice as well. So it was a sample, but it wasn't a living aquarium sample, which is what you need for physiology or growth incubations. What you really need to do is get on the ice yourself, and the ultimate here is to put a dive team in the water, but that's prohibitively expensive because of the amount of time required to make it safe, to mitigate the risks. They also can only deal with plankton. They can't catch a krill, which easily outswims a diver. So the other ways you can do it is you can drag nets, you can put light traps in, and the best way is actually to go tadpoling, and you can collect krill through holes in the sea ice like that in excellent condition, but you can't catch anywhere near enough to do useful science with them. So what we did is we got a 20-foot container and we took something from the salmon industry, a fish pump. This is a pump that doesn't chop up, and you can send a whole fish through the pump from one cage to another. And our intention was to put a tube down through the ice, suck the krill and water up through the fish pump, and then de-water them on a filter tray and have the catch in the tank afterwards. The PowerPoint's lovely for illustrating how a system works, but the Antarctic doesn't look like that. The Antarctic is a bitterly cold place to work in winter on sea ice. And even though we'd heat traced everything and insulated everything, the system still froze up during priming because the water was right on minus 1.81 as soon as it was coming up from underneath, and it would just freeze. So we quickly just put our head in our hands and went back on the ship. We set the system up in the CTD room, put the tube out the door. Even then it was a battle to even get the tube down through 4 metres of rafted sea ice. And plus we were now higher, so the pump had to run faster, more head height, and it was a much slower process. It did catch krill, and the krill were intact, but as soon as you pumped the krill out from an area, no more came in to replace them, so it was totally inefficient for what we were trying to do. So the following year, we set sail on Polarstern with the Germans into the Weddell Sea, because Polarstern has a moon pool. We put the same system on the science deck, and we put the inlet nozzle at the bottom of the moon pool. And this worked fantastically well. We caught krill larvae almost straight away, and we just left the system running for 9 days and revealed the first evidence of the inverted diel vertical migration of krill larvae, where they hide in the sea ice during the day, drop out at night, get moved along and come back up the following evening. And that was great because the krill larvae were also physiological specimens, undamaged. But because the pump was running so fast to cope with the head height, we were actually dicing the adult krill. So we hadn't quite cracked it. The other piece of evidence that really influenced the wet well is this beautiful piece of old equipment, the continuous plankton recorder. We've got a 30-year record now of continuous plankton recorder tows from Australia to Antarctica. And the reason we have that continuous record is because they cost nothing to run. They don't require ship time. And if you look at a continuous plankton recorder silk, as you can see in the background there, they even catch adult krill. And an adult krill can only possibly enter through that 1.2 centimetre hole if it is a bullseye shot down the line. It's an unlucky krill, but you see 5 of them right next to each other. And that's important information because it tells you if you just keep fishing and you hit high enough density, you will catch stuff, especially if the escape velocity of the animal you're after is 1 metres a second and you're moving at 6 metres a second. So speed is important. So putting all this together, we knew we needed a system that was operable all the time. It mustn't mechanically damage larger specimens, it must deliver them quickly, it must have access to the water column, and it must, above all, be a safe and comfortable working environment. So the solution was pretty simple. We just make some holes in the side of the ship and let the water in. But no captain in their right mind is going to let you do that to their ship. So the secret is to do it before the captain knows about it, before the ship even exists. And that is the opportunity Nuyina gave to us. So right from the very first day, we installed a wet well within the engine room, and it's below sea level. And that's important because it deletes the pump. It's the water pressure outside the vessel, the displacement of the ship that drives the water in. We placed it midship, so when the vessel rolls, it doesn't change the head pressure on the system. And we also worked in the ice modelling tank in Germany to put it in the position on the ship where the ice is cleared from under the vessel before we reach the wet well inlets in icebreaking trials. How does it work? Well, it's pretty simple. It's a hole in the ship. And we've got a surface, a mid and a keel intake controlled by hydraulic valves. Inside the wet well, we filter out the specimens, and the water falls through the floor into a tank and is pumped out at 7 cubic metres a minute. So it's an enormous amount of water. If a system blocks with ice, we introduce steam and push the ice back out or melt it out, whichever. The tricky bit is how you filter those animals out. And something that's robust with an exoskeleton, like a krill, you can filter out on a filter table. You just draw the water off them and they flip down into a tank. But we also want to work on all of that fragile plankton that comes onto the trawl deck usually in pieces. The sea butterflies, the salps, the things that ecosystem modellers need to have real physiological numbers on if they're going to make predictions about community shifts and changes as the ocean acidifies, warms, and we lose our ice. So to catch these, we wanted a viewing tank, which is an aquarium tank in line before the filter table, so we could detect their presence and shut the flow before they get filtered and remove them with a bag sampler. Now, this is a challenge to design because we're dealing with huge volumes of water which are freezing cold and contain ice slurries with particles up to 125 mils that have come through those intakes. And we turned to a New Zealander for this. This is Mike Murphy. He's an expert in acrylic engineering, and he designed the underwater hotel and restaurant in the Maldives, which perfectly fitted my bill for the sort of person with the knowledge to design that tank. And that's the tank in the top left, ready to be installed on Nuyina after the end of this current shipping season. But it's not just about the structure of the tank, it's also about the fluid dynamics. So we've got room for 2 of these systems in the wet well, so we can run 2 inlets at the same time. And my co-authors at the Australian Maritime College did the computational fluid dynamics on the flow. And if you look in the top right there, you can see the flow going from red to blue, where it's decelerating from 2 metres a second down to 6 centimetres a second in the viewing tank. The problem is that we found that when we looked at the particle typical flow paths, is they were all pressed against one wall of the viewing tank because of that 180 bend beforehand. So we had to change the inlet style and offset it and introduce a deflector. And that deflector allows us to smooth that path out and use the full length of the viewing tank to be able to spot those samples. So far, we've only tested the filter table, and this is from the commissioning voyage last year. This is a school of krill coming into the filter table. And the amazing thing is those animals were wild animals 4.5 seconds ago. And that's almost unprecedented in marine biology to have your sample in the lab that quickly. And there you can see a photo of them in the aquarium shortly after that. The survival rate is so good. It's gone from 10% with trawl nets to over 95% with the wet well because there's no opportunity to damage them. We also have ice ingestion, and in conditions like this, it's not an issue. You just get welcome samples of the sea ice that the krill were grazing on, not a problem. But if you're on the surface or mid-inlets and you enter fast ice, it becomes a big problem very quickly. And it's 40 litres a second of ice slurry in your lap before you realise you had a problem. But shortly after that, the whole system just blocks with ice. then you go down and open the steam valve, and 15 minutes later it's clear and running again, but you then switch to the keel intake, which is ice-free. When you're catching krill, they go into buckets. The buckets go into a lift, they go 3 decks above and go into integrated container aquarium. These aquariums are designed to maintain the seawater quality with new water from the ocean at the right temperature all the way back to Hobart. In Hobart, the integrated 15-tonne gantry crane in the back of the vessel unloads the containers onto the wharf where they're trucked, and commencing in September this year, we're building a new aquarium which is 5 times larger than our existing krill facility, where we'll work on those specimens. It'll be ready in 2027, and the key thing is it's being built around integrating to the Nuyina's aquarium containers. So as soon as they land there, they'll be plugged into life support, and the specimens can be disseminated into 17 different separate research labs. Now, this will be a focal point for Southern Ocean marine biology, not just on krill, as we've been doing so far, but also on these fragile specimens that previously are so hard to get hold of for that physiological work. And we want it to not just be an international focus for senior researchers, we want to make it the pathway for young scientists at the University of Tasmania, who we're building this with collaboratively, to train the next generation of scientists. So the next steps, we have to install that prototype viewing tank and see how good that computer fluid dynamic modelling really was, and we'll do that at the end of the year. And then we'll have a crack at extending it a bit further. We've already built this red pipe into the ship when we were building it, and it links the main science working deck with the wet well. And the concept here is you can have a hose reel on deck that you can deploy through Nuyina's moon pool or through the A-frame at the back to profile the water column down as long as your hose may be, probably up to 150, 200 metres. And by connecting the two together and then evacuating them, you create a siphon. And so the wet well can then become a profiling instrument. I mean, that's relatively straightforward and should work. I've said that before. But beyond that, we're going to try one step further, and we have a PhD currently running at the Australian Maritime College looking at a towed body working in the same fashion. And this is drawing rather a long bow, but it's a very interesting engineering challenge. And the concept is to have a towed body doing the same job as that hose reel. And we would have the EK80 echo sounder delivering to us the echogram of krill under the vessel. This is exactly how we target trawl krill today with nets, by running them in conjunction with the echogram. But we would adjust the position of this towed body, which is connected by this tube up to the vessel with hydroplanes, and steer through those scattering layers. It's highly ambitious, but the secret when you're building a ship is to build everything you want to future-proof it into the vessel at the start, because it's much harder to change a ship. So it's going to be an interesting space to watch. Thank you.
Amazing step change in our ability to sample. Do we have any questions for Rob? Charlie.
That's really, really amazing work. Have you guys thought about how you may use this study the system to study phytoplankton?
Yeah, we can already get our phytoplankton through the uncontaminated seawater line, so that's kind of taken care of. But what I'm really interested in is the sea ice capability delivery we have, because one of the problems when you collect sea ice on sea ice, you can freeze the sample in the air before you get it back on the ship. This just keeps delivering bits of sea ice and glacial ice that's dropped off icebergs perfectly. So we're putting a sea ice freezer on the vessel, and we're building a sea ice research freezer in that as one of those 17 labs in the aquarium. So this is a room we can chill down to -30, grow artificial sea ice, seeded with those samples from the wet well sea ice community, and actually have aquarium systems feeding on it. So, I mean, it's just a tool, and I'd like researchers to think of ways they can use it. And I see it as a tool that is a wet well, a containerised system, and the aquarium. It's one logistic flow chain, and that's what government should do. Government should supply systems that enable researchers to do this research.
Thanks, Rob. Anybody else got a question? Yes, up the back.
Thanks. This is really cool to see all the technical developments. I was wondering about this is bringing in lots and lots of water in for doing DIC measurements. I like to measure radiocarbon and DIC, and if this might be a really easy way to get surface water samples, collect larger amounts of water than we can in a lot of other systems. I wonder if you've thought about the integrity of the water and changes when the sampling comes through.
Yeah, I did think about that when we were specifying the vessel, when writing the functional performance specification. I initially wanted to build the whole thing out of something really inert, so we wouldn't change the chemistry of water coming in, thinking like something like this. But I was overridden by cost at some point on that project. I think we got just about everything we asked for on that vessel. It was magnificent. But it is just a galvanised pipe leading into the lab, but there is absolutely no problem to give you huge volumes of water should you desire it for a purpose. It won't make a difference to the sampling we're doing. It's 2.5 tonnes a minute through each of those lines, so it's plenty to spare as long as you don't mind it running through a galvanised tube. And the other thing is, of course, the galvanised tube is open to biofouling, but as soon as you run the first piece of ice through a tube, it's beautifully clean, and you can have a mussel or an oyster in the lab.
Fantastic. Thanks again, Rob.